60,000 times slower Python code isn't just an illusion or something to get clicks. It's a real problem that was demonstrated by Dr. Patterson in a paper he wrote called There's Plenty of Room at the Top: What Will Drive Computer Performance After Moore's Law. This appeared in Science in June 2020, and I also was able to go to a talk where he talked about this in person as well. And it really got me thinking about this concept of the end of Moore's Law and some of the things that are happening as a result of that. I think if you look at the automobile industry, you can see that it also did some of the same things that the computer industry did. So let's say in the late 1960s, people were building these muscle cars and big cars like Chevy Suburban that got a few miles to the gallon, or Ford Mustangs, and they were just guzzling up gas. And that was okay for a little bit when gas was really very cheap. We didn't know as much about climate change, and also we were able to really deal with it by just making bigger and bigger engines. But eventually we got to the point where we realized that, in fact, that original architecture needed to be improved. That's why Japanese cars came in and started to make huge headway for their efficiency. And then later we got, turbocharged cars and diesel, and eventually now we have zero emission cars in terms of electric engines. So we see this history of iteration, right, with automobiles. So we see the same thing with the chip industry, where the physical miniaturization maybe gave people a false sense of confidence initially, like in the 90s when Python was invented and these scripting languages started to take over, that we thought, oh, look, we don't really care about performance. We're almost like the American automobile manufacturers. The performance is going to double every 2 years. Let's just keep on doing things where we don't care about that performance. But as noted in the paper and also in the talk that I attended, that there are some shocking problems, and that there are no more doubling every 2 years. We're basically flattened out. And so what is the way to get gains? Well, there's plenty of room at the top. And what this means is that if we look at how Python itself is potentially part of the issue, it showed that basic matrix multiplication in Python takes 7 hours on the equation that was listed. So it's basically a bunch of nested loops, but the same code optimized runs in about a half a second. So this is a 60,000 times improvement just from better engineering. And you can see this is a huge gap in modern languages, is that they have these inefficiencies built in, and we haven't really thought about the C-level performance or better than C-level performance as a priority. And part of this is because I think we were fooled into saying that developer time is more important than runtime. And I don't think that's the case, especially with some of the advances with coding assistants that we're seeing in 2025. So let's talk about 3 of the major areas for future gains. Like, one of them is that we could look at software performance engineering and look at this bloat that's been in a lot of these languages. So interpreted languages are really designed for you to have a feedback loop with the language and try things out. But why are we putting that artifact into production software? Why don't we design things so that they're high performance at the very beginning, right? Like, why wouldn't we design things so they run at greater than C-level performance? And also, as mentioned in the paper, you can go even beyond that. So if you go into a specific kind of parallel loop, maybe you could get a speed up of 366 times. If you go into parallel divide and conquer, so you start to get into these algorithms, going into vectorization, you get into chip specific features, you could get into a 60,000 times increase. And so really the idea here is that the speed up, with a compiled language like Java, that's an older, slower language, you can get maybe 11 times. You go to C, we're getting 50 times performance. But why stop there? Could we even get into mixing new algorithms, new hardware, and new languages together? And I think that's what's really interesting about thinking of the future and the future languages. So one of the ways that you could do this is that you could look at large code bases potentially as a first place to start. And then in terms of algorithmic improvement, some algorithms will match and exceed Moore's law. You can look at also the maximum flow problem. So could you get a 10,000 times speed up just from a better algorithm? This is the classic, O to the N, etc. problem. Also, look at new domains like AI and ML. Are there different ways to combine all these approaches? And then also, could we make new algorithms for modern parallel hardware? And then in terms of the hardware architecture itself, thinking about by design moving things outside of a single core to these specialized processors, like for example Google has a TPU or their ARM processors. Graphics GPUs are now in 40% of laptop chips, and you can see that you could even develop more and more specific hardware accelerators for specific use cases. Maybe you could have a hardware accelerator for large language models or small language models or embedded small language models. So the reality is that this idea that you're always going to get future gains from Moore's law is gone. And we've known this now for quite some time. And the improvements are going to be opportunistic. They're going to be domain specific. They're also going to require significant engineering effort. And we also know that there'll be diminishing returns over time. This is part of the arc of innovation. So you're going to need to coordinate across all of these different aspects. So not only the software, again, going from an interpreted language to a modern compiled language, but also the hardware layer and also the algorithmic layer. So some of the key components here would be, large scale systems. Also, single ownership could allow a very coordinated improvement. So if you're able to build something that really goes from the beginning to the end, you're building the software language, you're building the algorithms, and you're building the hardware. That's a very interesting way to get the efficiency. Some examples could be web browsers, databases, operating systems. And if we look at also maybe economic incentives, as if let's say that there's a huge crash in the future with overdevelopment of AI, maybe one of the ways that we will start to improve is people will look for cost savings. And that's when you start to look at this single stack improvement, where a single owner could build these kinds of solutions where the whole language is designed for efficiency from the very beginning. So really the near term gains are going to come from engineering, right? You can just use better languages. And I think we're seeing this with Rust, with Go, maybe languages like Zig. Also, rethinking the software development priorities as well, and looking at performance engineering. And I think this is really the big takeaway, is that if you look at before, let's say 2024, 2025, there was a lot of emphasis on, hey, let's just throw developers at the problem. But now we're seeing that code, I guess generating code is becoming easier and easier with large language models. It doesn't mean the code is good though. And also we need to have experts who really understand performance and optimization. So what could happen is that really we start to see over the next 5 to 10 years, people thinking about performance much more, and that it's not acceptable to ever push code into production that is slower than C. And you could even make the case where we need to start looking at ways to go faster than C. So a recent example of this would be that I was experimenting with the new language Zig, which has been touted as a modern replacement for C. And I was able to get a 16 kilobyte web server running inside of a Docker container that was a Scratch container. And if you look at what that would do in production, I mean, it's amazing because the language has no runtime overhead, really. It just immediately starts. You can see it's very tiny. So when it needs to launch from some kind of container service like Kubernetes, etc., it's going to be very tiny. And all of these optimizations make it very compelling to even think about different architectures. For example, could web applications call into 10 or 15 or 20 of these really tiny containers? Why do we actually care about JavaScript performance? Maybe we could care about WebAssembly performance. So really, to summarize things here, is that now that we're in a new era with new tools, the modern compiled language, I think, is going to get more and more attention. And just because older languages were more popular, like Python, That doesn't mean the past will predict the future. It's really a new era now for software development. And I personally am trying to never write code that is slower than C.